Hello, my name is John Fortner, and this is my report on Lab 1, Charge Tapes. So the goal of this first lab was to find the charge on an object that is experiencing zero net force by comparing the force on the charged object to the gravitational force acting on that object. So we rely on the momentum principle because we have to understand that it has zero net force, meaning it has zero acceleration in either direction. And then we also use the formula for electric force, which we can then use to calculate the charge on the object. So here we have some observations that we made during the experiment. So we found that the mass of one tape is 0.1968 grams, and the distance between the two tapes when one was floating above the other was 15 centimeters. And then we found that the tapes had a positive charge, which we deduced by the fact that it was attracted to a negatively charged pen. So from those measurements, we could find the gravitational force on the tape by multiplying the mass times the acceleration due to gravity times the y hat direction, which gave us the vector 0, negative 1.9306 times 10 to the negative 3 newtons. And from that, we could deduce the electric force on the tape, which was an equal and opposite force, because we could observe that the net force on the object was 0, because it was floating without any motion. So here we assume that the two tapes have the same charge, and from that we can rearrange the formula for electric force to obtain a formula for the charge Q of each of the tapes. And from that we calculate and get the value 6.9473 times 10 to the negative 9 coulombs. So here we need to calculate the number of electrons, and because it's positively charged, we know that the tape has a deficiency of electrons. So here we divide the charge of the tape by the charge of an electron, and we can see from that the charge on the tape is equivalent to a deficiency of roughly that number of electrons. Here we divide the area of the tape by the area of an atom to get the total number of atoms on the tape, and then we can divide the number of electrons by the number of atoms to get the deficiency of electrons per atom, which is in this case 1.8 times 10 to the negative 9 electrons per atom. So here we have the results of my code, and as you can see, the top tape tends to oscillate very, very close to 15 centimeters. As you can see, this axis is barely reaching very infinitesimal decimals. So this is exactly what we should expect, and I'll talk about why it oscillates in a minute. But the important thing is that the charge tends to stay around this point at 15 centimeters rather than going up or down in one significant direction. It sort of just floats above the other charge. And here is the way I accomplished this model. Here I establish the initial conditions of a bunch of variables that I use in the calculations, and then in this while loop I have a force of gravity. I have here an electric force, all that I calculate along through the loop, and then calculate the net force, and then use these velocity and position update formulas to update the position of the sphere. And then after that, I append it to the graph and then print the graph. And what you can observe from this model is that the charge tends to float above the other charge, which is exactly what we should expect to happen. So this model confirms, as was predicted, that the charge on each tape is roughly 6.9473 times 10 to the negative 9 coulombs. But to do this, we had to make the following assumptions. So first, we ignored air resistance, and that's the reason that we had this constant oscillation rather than the point charge coming to a stop at a certain position, because without an air resistance, acting on the point charge, there's nothing to stop it from just going up and down forever. But the important thing is that it oscillates about that expected position. And then we also treated both tapes as point charges with all the charge concentrated at the center, which is why we use spheres. And then we also assumed that the two tapes had the same amount of charge, because if they had a slight difference, then it would have changed the amount of electric force acting on the top charge. So here I answer some additional questions. So first, what if electrons had a positive charge and protons had a negative charge? Well, in this case, the tapes would have acquired a negative charge because they would have actually, they still would have lost electrons, which having a positive charge would have given the tapes a net negative charge. So in our case, in our actual experiment, the results would have been the same because the tapes would still have the same charge and would still repel each other. But in the observation phase, they would have been repelled by the negatively charged pen as opposed to attracted by it, as they actually were in our experiment. And then why is it important to handle the charged tapes as little as possible? Well, when the tapes come into contact with the human body, the charge is conducted through the body to the earth and is grounded. So as a result, the tapes lose charge when they're handled, becoming more and more neutral the more you touch them. So it's important not to handle them too much so that you can have good results and the tapes maintain their charge. And that's all. Thank you for watching.